Okay, so this will be the second example on settlement in clay. So we're given a soil profile at a site that consists of 6 meter thickness of gravel, as we can see here. However, this gravel is divided as 1 meter dry and 5 meter wet. That's below the water table. So, and there's a note at the bottom that says you should assume that the gravel above the water table is dry with a unit weight of 16, and the one below the water table is saturated with a unit weight of 19. Okay. Then a sample taken from the mid depth of the clay. We took a sample. Okay. Right from here, and this sample gave us the following properties. Gave us that the moisture content is 23%. The total unit weight is 18%. The compressive index is 0.4 and the recompression index is 0.1, and the pre-compression stress is 100 kPa. Okay, so the following construction sequence is then to be rapidly carried out. What would happen actually? That they will excavate the first half a meter and keep only 5.5 meters of gravel. Then we will lower the water table to the interface between the gravel and the clay, and we will apply a surcharge. So three things are happening. We are excavating the top, so less gravel, the water table is lowered, and a surcharge is added. Okay, so whenever we have two-stage problems, I always like to calculate the stresses before I even read the question. Okay, so let me show you that. Okay, so let's say at stage 1, before construction, my effective stress, or actually my total stress for now, is equal to 1 meter of gravel, dry gravel, plus 5 meters of wet gravel. And then, since we're taking the sample in the middle layer of clay, that means we are 1 meter inside the clay, right? We are 1 meter inside the clay. So, total initial stress is going to be 1 times dry gravel unit weight. Dry gravel unit weight is 16 plus 5 times wet unit weight, which is 19, plus 1 meter of clay, which is given as 18, and that will give us 129 kilopascals. Then to find the effective, I must find pore water pressure, which is defined as from the point of interest up to the water table. So we have 5 meters plus 1, we have 6 meters of water times 9.8. That will be 58.8 kilopascals. Finally, my effective stress is 70.2 kPa. Okay. Then we've moved to stage 2. Let's call this final stress. Now we have the final stress. Okay, so here we have 50 kPa surcharge plus 5.5 dry gravel plus 1 meter of clay. So that would be the dry unit weight is 16 plus 1 meter of clay, which is 18. $156 kilopascals. Pore water pressure is defined from water table to the point of interest, which is 1 meter. Therefore, my effective final stress, is 146.2 net kPa. Okay, so we are expecting, if I draw a diagram, initially our stress was at 70.2. Okay, then and we had initial void ratio. Then, since sigma dash naught is less than sigma dash pc, okay, which is 100, we would be following the recompression line. Okay, so here we have sigma dash pc. Then once we cross the sigma dash pc, which is 100 kPa, we would change into a different slope. Should be a straight line. Oh, that's as good as could be. That would be CC, and that would be CR. And here is my final, which is 146.2. Okay, because we're moving from this point of stress, but we have to pass through sigma dash pc, so we have to change the slope. Okay, now as the last example we did, okay, we could break this down into two, part 1 and part 2. Let's call this one delta E1, delta E2, and delta E total, which is what we need, is delta E1 plus delta E2. Okay, delta E1 is following the recompression line, so I can say that CR equal difference in height, which is delta E1, over difference in stress, which is log sigma dash pc over initial. Therefore, delta E1 equal to CR log sigma dash pc over sigma initial, and I consider delta E2 or CC equal delta E2 over log sigma final dash over sigma pc dash. Therefore, delta E2 equals CC log sigma final over sigma pc. Finally, delta E equal CR log sigma pc dash over sigma initial plus CC log sigma final dash over sigma pc dash. Substitute sigma r was given as CR equals 0.1 and CC equal 0.4. So this is 0.1 log sigma pc dash 100, sigma initial is 70.2 plus CC is 0.4 log sigma final, which is 146.2 over 100. That is equal to 0.08, ah, sorry, 81. Okay, now I could say the settlement will be consolidation at time infinity equal to initial height times difference in void ratio over 1 plus initial void ratio. Height was given as 2 plus difference in void ratio 0.081 over 1 plus E naught. Now E naught is not given, it's not explicitly given, but we're given the moisture content. You'll be wondering, what are we going to do with the moisture content? Well, we all remember the famous formula that George Washington was a civil engineer, right? Specific gravity times moisture content equal saturation ratio times the void ratio. George Washington is a soil engineer, was a soil engineer. So the saturation ratio is 1 because saturated water, which would leave us with void ratio equal specific gravity times moisture content. Specific gravity always assumed to be 2.65. 2.65 times moisture content is 0.23. Therefore, initial void ratio equal to 0.609. Let's use this value now. Sorry, that's multiplication. That's multiplication. Is 0.1006 meters. So this much the soil has settled. That means my final soil height is my initial soil height minus my settlement. Initial is 2 minus 0.1106. That would be roughly 1.9. Okay, or I could actually say exactly 1.899 meters. Okay, and that's the end of this question. Thank you.